For example, here this reaction, hydrogen plus iodine to produce 2 moles of hydrogen iodide. Here, step number 1, or in case number 1, it may be here, iodine first dissociate to 2 iodine atoms, then 2 iodine atoms react with hydrogen to form 2 moles of hydrogen iodide. So when you add these equations to each other, you can delete it here because here in the products and here in the reactants. So the net equation is iodine plus hydrogen produce 2 moles of hydrogen iodide. So here in the equation, the first step, iodine dissociate to 2 iodine atoms, then 2 iodine atoms reacts with hydrogen gas to produce 2 moles of hydrogen iodide. So this is called the activated complex. Or another mechanism, maybe here iodine dissociate to 2 iodine atoms, then the first iodine, here direct, 2 iodine atoms react with hydrogen. Here, the first iodine atoms react with hydrogen to form dihydrogen monoiodide. Then H2I reacts with the second iodine here to CO2 iodine. Here the first one and here the second one to form the product. So when you add these equations with each other, you form the chemical equations. Hydrogen plus iodine form 2 moles of hydrogen iodide. So here in chemical equations, you don't see some substances. These substances that do not appear in the net equations are called activated complex or intermediate. So again, for these reactions to occur, the reactant must be transformed to the activated complex, then activated complex transferred to product. So this is the activation energy. Energy needed for a reactant to transform to the activated complex. Again, the minimum energy needed for a reactant to transfer into an activated complex. So the reactants transform to activated complex, then activated complex transform to product. Again, in the net equation, you can't see the mechanism of reactions or how the reactions or what are the steps of the reactions. And in the net equations, you can't see the activated complex because activated complex or intermediate deleted when you add the equations to each other, and here the net equation. So if you want to draw again the energy diagram here, two energy diagrams for endothermic reaction and exothermic reaction. So here, as you remember, for endothermic reactions, energy of reactant greater than for endothermic less than energy of product. So delta H, if you remember, it's positive. Or here for exothermic reactions, energy of reactant here greater than energy of product. So here delta H is negative. So here in endothermic reaction, energy of reactant less than energy of product. So when you draw the energy diagram, here the reactants, for example, and here the product. So energy of reactants less than energy of a product. This is the energy diagram. So again, what is the top of the curve? It's an activated complex. So first, reactants transform to activated complex, then activated complex transform to product. Here in exothermic reactions, the energy of reactants greater than. So here, for example, here the reactant and here the product. How to draw the energy diagram? Here, like this. This is the top activated energy complex. So for here, some questions ask about the activation energy or activation energy for the forward reaction, or maybe ask about activation energy for the reversed or backward reaction, or it may be asked about difference in energy or delta H. So how you can get activation energy for the forward reaction or activation energy for the reverse or backward reactions, or delta difference in energy or delta H from the diagram. Here, if you remember the definition of activation energy, it's the minimum energy needed for a reactant to transfer to activated complex. So the energy difference between reactants and activated complex, it's called activation energy. So activation energy is the energy difference between reactants to activated complex. What about activation energy for the backward reaction? It's the energy backward or reverse reaction as a product become reactants and reactants become product, reversed reaction. So the activation energy here, it's the difference between energy of a product and the activated complex. Here, activation energy for the reversed reaction. Now what about delta E? Difference in energy, or delta H. It's the energy difference between reactant and product. So what is the energy difference between reactants and product? This is delta E. Energy difference between reactant and product. So the same for exothermic reaction. What is the activation energy? Energy difference between reactant and the activated complex. What is the activation energy for the reversed reaction? It's the energy difference between a product and the activated complex. What is delta E, or difference in energy, or delta H? It's the difference in energy between reactant and products. So here, if you have a question, for a reaction X plus Y, these are the reactants produced, W and Z. These are the reactants, and here the products. So what is activation energy for the forward reaction, activation energy for the reversed reaction, and delta H or delta E. Here you have energies. So what about activation energy? It's the energy difference between reactant and activated complex. So where is the activated complex in the diagram? At the top. So here, activated complex. So what is the activation energy? The energy difference between reactant and activated complex, which is equal 80 kilojoule. Now what about activation energy for the reversed reaction? It's the energy difference between products here and the activated complex, which is equal 33 kilojoule. Now what about delta H or delta E? Difference in energy between reactants and products here. What is the energy difference between reactants and products? So if you subtract 80 minus 33, you can get delta E. Again, difference, delta H or delta E, it's the difference of energy between reactants and product. So here, you have to subtract 80 minus 33 to get delta H. So here, 80 minus 33, which is equal 47 kilojoule. So again, this lesson talk about the rate of reactions. Rate of reactions means speed of reactions. So to get the speed of reactions, you have to find the energy diagram here, and reactant with lower activation energy, so it has the higher rate of reaction, and reactions of higher activation energy, so the rate of reactions decreases. So a theory that talks about the rate of reactions, it's called collision theory. It has three assumptions. The first one, particles must be collide with each other for a reaction to occur. Particles must be in correct orientation for a reaction to occur. And assumption number 3, particles must have enough energy for a reaction to occur. Enough energy, how much? It's equal to the activation energy, which is the minimum energy needed for a reaction to occur, or it's the minimum energy needed for a reactant to transfer to the activated complex. So what is an activated complex? It's substance that do not appear in the net equations. It appears in the mechanism of the reactions, and mechanism means step-by-step sequence of reactions. And the last thing, here, if you have energy diagram, the questions ask about what is the activation energy for the forward reaction, what is the activation energy for the backward reaction, and what is the delta H or difference in energy. So activation energy is the difference of energy between reactants and the activated complex. And for the reversed reactions, it's the energy difference between products and the activated complex. And delta H or difference in energy equal the difference in energy between a product and reactant. Thank you.